Hyperparameter tuning for multi-level classification of feedbacks in online courses. Introduction. In this work, we propose extension of a methodology for the multi-level classification of feedback according to the Haitian-Template feedback model, incorporating a hyperparameter tuning stage. It is analyzed whether the incorporation of the hyperparameter tuning stage prior to the execution of the algorithm support vector machines, random forest, and the multi-level nearest neighbors, improves the performance metrics of multi-level classifiers that automatically locate the feedback generated by the teacher to the activities sent by students in online courses on the Blackboard platform at the task, process, regulation, phrase, and other levels proposed in the feedback model by Haiti and Temporally. Feedback. The feedback refers to comments that a teacher provides to the activities that a student delivers to inform them about their performance or level of understanding when performing a task. Formal definitions of feedback found in research literature are information provided by an agent about aspects of someone's performance or understanding. A product resulting from the review analysis by the teacher of the activity, contribution, or product that the student hasn't. Feedback is an important element in the learning process of students. This helps the students evaluate their learning progress. It empowers the student to identify and solve their misconceptions, thereby improving their performance. It provides the student reflection on their actions and consequences, allowing them to reach goals and objectives. It has been identified that poor feedback can cause problems in study learning and even lead to dropping out of school. Methodology for multi-level feedback classification. In a methodology is proposed to analyze the quality of feedback extracted from evaluations collected from online courses from a curriculum offered at a university in Mexico. The authors use multi-level classification, which is a predictive task that relies on machine learning algorithms to learn from label patterns a model capable of predicting the label or class for future examples. They make a comparison of the transformation and adaptation multi-level classification approaches. They use random forest, support vector machines, logistic regression, a-based multi-level k-nearest neighbors, and multi-level support vector machines algorithms for automatic feedback analysis. The author used these levels proposed in the effective feedback model by Haiti and Temperley. They evaluate multi-level classifiers using data set containing 11,013 feedbacks manually labeled by online education experts at task, process regulation, phrase, and other levels. Their results indicate that the transformation approach allows a better classification of feedback than the adaptation approach. The algorithms that best classify the feedbacks are the vector support machines and random forest, when using the transformation approach and the multi-level k-nearest neighbor algorithm for the adaptation approach. The methodology proposed does not consider a hyperparameter tuning stage that could improve the performance of multi-level classifiers. Hyperparameter tuning. Hyperparameters are parameters that are not directly learned in classifier training and must be passed as arguments before using a classification algorithm. Hyperparameter tuning refers to the task of finding the optimal hyperparameters of a learning algorithm for a considered dataset. An optimal hyperparameter will be the one that achieves better values for a specified performance metric. The importance of hyperparameter tuning is that the performance of various classification algorithms has been shown to depend on the settings of the hyperparameters that can make the difference between a good or bad classification. Hyperparameter tuning strategies. To select an appropriate hyperparameter configuration for a specific dataset, the default values provided by software packages are often used or configured manually based on recommendations from the literature, experience, or trial and error. Another alternative is the use of strategies for the tuning of hyperparameters that are dependent on the data like grid research, random search, and model-based sequential optimization. Methods for performing hyperparameter grid search, a strategy in which all possible combinations of given discrete parameter spaces are evaluated. Random search, a strategy in which the values of the hyperparameters are obtained randomly from a specific space of hyperparameters. Model-based sequential optimization, adjustment strategy that iteratively tries to find the best values of the hyperparameters based on evaluations of the hyperparameters that were previously obtained. Extended methodology. The extended methodology proposal incorporates a hyperparameter tuning stage to the methodology, of which must be carried out before the classification stage. The extended methodology proposal incorporates the hyperparameter tuning stage to the methodology, of which must be carried out before the classification stage. The hyperparameter tuning stage has the purpose of finding the best parameters for a classification algorithm. The best parameters will be those that got the best value for the metric. Data integration gathering. The same dataset of 6 was used, which contains feedbacks written in Spanish, generated by teachers who published them through the task review tool in the Blackboard Learning Management System. The dataset is composed of 11,013 feedback collected from 121 online courses from a degree in law in a public university in Mexico. Each feedback were manually classified by experts in online education following the feedback model by Harry and Timperley, locating each feedback at the task, process, regulation, praise, and other levels. The multi-level dataset was partitioned in two subsets, one for training and the other for testing. Table 3 table show. Table 2 shows the distribution of feedbacks in the training and test sets for each level, showing the number of feedbacks belonging or not to the level. Table 3 shows the characteristics of the training and test sets, in which cardinality counts the number of average labels relevant to each instance. In the dataset, density refers to the cardinality normalized by the total number of all possible labels. Mean IR obtains the radio of the most common versus the rarest label, and the Campbell value measures the concurrence between frequent and rare labels. Preprocessing and calculation of TF-IDF. Each feedback was removed. HTML, CSS codes, characters other than words and digits were removed. Digits, web addresses, and file names were replaced by identification keys. They went to lowercase. Lemmas were obtained for each word. A spell checker that uses Levenstein distance was applied for words with frequency less than 10. Top words were removed. Truncation was applied to each word, and words with a frequency less than 10 were eliminated. Then each feedback was converted into a term document matrix representing the frequency of each word in each feedback. The TF-IDF value is used. It combines the termination frequency and the inverse frequency of feedback by multiplying the local frequency weight of each feedback by the inverse weight of the feedback. Hyperparameter tuning. The hyperparameter tuning stage has the purpose of finding the best parameters for a classification algorithm. The best parameters will be those that got the best value for the metric. The algorithms considered in this work were the support vector machines, random forest, and the multi-level nearest neighbors, as they were the ones that achieved the best performance in the task of locating feedbacks according to the proposed levels by Harry and Timperley. The hyperparameters considered for each algorithm at the space parameter used are shown in Table 4. The regularization parameter C and number of trees that may exist in the forest are explored for the algorithms of support vector machines and random forests respectively. For the multi-level k-nearest neighbors algorithm, two hyperparameters are explored, which are the number of neighbors to take into account and the smoothing parameter S. Classification. In this stage, the classification algorithms are executed in order to train multi-level classifiers that learn from the test set that contains the manual classifications of the feedback carried out by the experts. Each algorithm were executed by default hyperparameters. 14 multi-level classifiers were trained, 7 following the methodology proposed in 6th, and 7 with extended methodology. For each methodology, tests were performed using the transformation and adaptation multi-level classification approaches. For the transformation approach, binary relevance, classifier chains, and power set were used. Table 5 shows the trained multi-level classifiers grouped by methodology, multi-level classification approach, used algorithm, and transformation method. Analysis and evaluation. Each multi-level classifier is provided with the feedback of the test set without the classifications made by the experts so that they can automatically classify each one according to the proposed labels by Harry and Timberlake. Then they compare the automatic classifications performed by the multi-label classifiers with those classified by the experts through the calculated multi-label classification metrics. Evaluation of the extended methodology. The performances of multi-label classifiers following the methodology of six were compared with those of the extended methodology. Those trained with the six methodology used the default values of the algorithms. The training and test datasets from six containing the prepreset feedbacks and manual classifications performed by experts were used. Each preprocessed feedback was passed into a document term representation using a bag of words and gram, as these were the characteristics that allowed to achieve better performance in the multi-label classification metrics in 6. Results: the default hyperparameters that each algorithm has and those obtained from the hyperparameter search stage are shown in Table 6. For the support vector machine algorithm, the best value for the accuracy metric has to be is achieved when the regularization hyperparameter C has a value 100. For random forest, the number of trees to have the best accuracy in the training set is 400 when using the binary relevance transformation methods and classifier chains. For the power set, a value of 500 should be had. For the multi-label k nearest neighbors algorithm, the value k 8 and s 1.0 are obtained as the hyperparameters that achieve the best accuracy for the training dataset. Table 7 shows the performance metrics achieved by each classifier using default values and the use of fine-tuned hyperparameters evaluated with the validation set. The arrows in each of the metrics indicate whether a high or low value is better. From the analysis of the results, it is detected that the classifier that best achieves this objective of automatically classifying the feedback at the task, process, regulation, praise, and other is the one that uses the transformation approach, with the support vector machine algorithm using fine-tuned hyperparameters and the data transformation method binary relevance. The multi-label classifier manages to have only 7.4% of all labels misclassified with respect to what is labeled by the experts as indicated by the Hamilton's metric. A good balance of precision and competitiveness is achieved by obtaining a value of 87.1%. For the accuracy metric, it is possible to have 72% of the feedbacks with the 75 well classified labels. Also, it achieves an acceptable precision by achieving 93%. It is observed that when the transformation approach is used with the support vector machine algorithm with fine-tuned hyperparameters and the power set transformation method, the best values for the average precision and accuracy metrics are achieved. However, this classifier is not left as the first option since in the multi-label training data set there are only 23 of the 32 possible combination of labels. Similarly, it is noted that the use of hypertuned parameters improve the performance metrics of the multi-label classifiers regardless of the approach, algorithm, and transformation method compared to the use of default values. It is noted that the training time of the multi-label classifiers will be longer when using the hypertuned parameters compared to the default parameters. Training time. Regarding time, figure 2 shows the seconds it took to train the multi-label classifiers when using default hyperparameters of the algorithms and those found in hyperparameter training stage. It is shown that a hyperparameter training stage will significantly increase the training time of the classifiers. Conclusions. In this work, a methodology for the multi-label classification of feedback is expanding according to the feedback model by Haiti and Trimpley, incorporating a hyperparameter tuning stage. It is shown that the incorporation of the hyperparameter search stage prior to the execution of the algorithms allows improving the performance metrics of multi-label classifiers that automatically locate the feedback generated by the teacher to the activities sent by students in all courses of the Blackboard platform at the task, process, regulation, and praise levels proposed by Haiti and Timberlake. Comparing the multi-label classifiers that use the default hyperparameters and those obtained from the hyperparameter tuning stage, it is evident that the same or better metrics are obtained when using tuned hyperparameters. It is observed that fine-tuning the hyperparameters to improve the accuracy metric will allow the improvement of other multi-label classification metrics. The hyperparameter tuning stage improves the performance metrics of multi-label classifiers. For example, for accuracy improvements greater than 3% are achieved. Although performance metrics improve, it is important to consider training time, which has a significant increase when using hypertuned parameters. As future work, we will analyze whether the use of other features such as POS tagging or word embeddings can improve the performance of the classifiers.